Okay, so in this lecture, we're going to learn a new technique for computing integrals. It's called integration by parts. But the first thing we're going to do before we get started is just kind of think about what's happening here. Okay, I want you to kind of think before we just, I just give you a formula and you start plugging things in. All right, so let's say we want to compute this integral from well, it's just an indefinite integral of x e to the x dx. Okay, now this isn't really a candidate for substitution, because I don't see anything where we can, where we can split this and one part looks like the derivative of another part. So, but it does, I'm seeing the product of two functions, right? I have the product of x and e to the x, which makes me think, okay, well, I know there's a product rule for derivatives, so I wonder if there's some way that there's some kind of product rule for integrals, or maybe from the product rule for derivatives, we can figure out some way to compute the derivative of this product. So let's see, I know the antiderivative of x is like x squared over 2, and the antiderivative of e to the x is e to the x. So let's just try something here. Now, I want to find an antiderivative. So I want to be able to take the derivative. If I take the derivative of the antiderivative, I should get this function that I'm trying to integrate, right? If I take the derivative of the antiderivative. So let's just say, let's just pick a function, and that kind of looks like it has the components we need. And let's take the derivative of it. So if I integrate, or sorry, if I take the derivative of e or x e to the x, okay, I'll take the derivative of that. What do I get? If I use the product rule, I have the derivative of the first. Okay, the first is x, so that's just 1 times the second, which is e to the x, plus the first times the derivative of the second, which is e to the x. All right. So I'm seeing here, I took the derivative. I didn't get exactly what I'm looking for, but part of it looks good. So let's see what happens if we integrate both sides. I'm going to integrate the derivative of x e to the x dx, right? And if I integrate the other side, I have a sum of two things. So I'm just going to do the sum of the integrals. So I get the integral of e to the x dx plus the integral of x e to the x dx. Now this is what I want, right? This is what I want. So if I can rearrange this a little bit, maybe I can actually get what I want. All right, so I'm going to rearrange this. I'm going to solve for the integral of x e to the x dx, right? And then what I'll end up with is let's see what I'm going to do. I'm subtract this. So I'm going to get the integral of d dx, x e to the x dx, and then minus integral of e to the x dx. Okay, when I rearrange that. Now, the integral of a derivative just gives me back the original function. All right, so I'm going to rewrite this over here. Integral of x e to the x dx is equal to, so this first thing just becomes, the integral of the derivative just becomes x e to the x, and then minus the integral of e to the x dx, and that's easy, right? Integral of e to the x is just e to the x, so I get, this is x e to the x minus e to the x. And then, of course, because it's an indefinite integral, I have to add the plus c. Okay, so that's the integral. Now that was not it was sort of a guess. I just sort of started with a guess here, right? I just started with a guess and tried to apply the product rule to get something that looked like what I'm looking for. So this is not integration by parts yet, but this is just a little bit of a background of where it's coming from. So I'm going to look at another one here. It's very similar, all right? Only now we're trying to integrate theta cosine theta d theta. So again, I'm just going to try a guess first and then see if I can rearrange it to get what I want. All right. So this looks very similar. So I'm thinking, okay, product rule. But in this case, the derivative of, the antiderivative of cosine is sine, right? So let's try this. Let's try d theta. Let's try theta sine theta. Okay, because I know if I take the derivative of sine theta, I get cosine theta. So and I have a product here. So let's see what happens when I take the derivative of that. I get sine theta, right? So it's the derivative of the first times the second plus the first times the derivative of the second, which is cosine theta. Okay, and voila, look at that. Theta cosine theta. That's what I want. So I'm going to do the same thing I did before. I'm going to integrate both sides. Theta sine theta d theta, right? I'm going to integrate sine theta d theta and integrate theta cosine theta d theta. Okay, so I just took the integral of both sides. And, okay, so this is what I want, right? This looks good. I like this a lot. It matches with what I want. So I'm going to rearrange just like I did before. Integral of theta cosine theta d theta then is equal to the integral of this derivative with respect to theta. Theta sine theta d theta, and then minus the integral of sine theta d theta. Okay. All right, so this is what I want. So I'm going to rewrite it up here. I'll write it here. Integral theta cosine theta d theta is equal to, now I take the integral of the derivative, and that just gives me that function theta sine theta, okay, minus the integral of sine theta. Okay, so what's the integral of sine theta? It's minus cosine theta, right? Because the derivative of cosine is negative sine, so so the integral of sine is negative cosine. So we're going to get minus a minus cosine, so it becomes plus cosine of theta plus c. And what do you know? There we go. That's it. That's my I done it. I did it. It wasn't pretty, and I don't like the fact that I have to start with a guess. So I want a little more systematic way of doing this. So that's what I'm going to talk about next, before I go into the next example and demonstrate how integration by parts works.